So let's go straight to our first talk. So our first talk will be by Juliana Garcia-Mejía, who's going to tell us about the Tierras Observatory. I'm not going to read the whole title because I don't want to use up your time. So.
Great. Thank you, everyone. My name is Juliana Garcia-Mejía, and I am a first-year fellow. And before I get started and tell you about the Tierras Observatory, I really did just want to take a moment and thank Neil and Jane. This is just such a special place. I'm so excited to be here, and we're so grateful for your generosity. You quite literally, like Matthew said, welcome us into your home every year and create this environment where we can grow personally and professionally every week. I am growing and learning from faculty at the department when I meet for them for lunch on Wednesdays and Thursdays. And I think that's a really, really special and unique aspect of this fellowship. And I'm very excited to tell you about the intellectual pursuit that I am most excited about, which is the development of novel optical and near-infrared instrumentation to search for exoplanets, or planets outside of the solar system. Because as I'm sure many of you may have heard, over the past 25 years or so, we've discovered something like 5,600 and something planets, most of which come from the Kepler Space Telescope, which was decommissioned in 2018, but an increasing majority which come from the MIT-led TESS mission, which for sure will become the majority in a few years' time based on the amount of candidates we have. And there's a very interesting picture that's emerging from studying these planets in a demographic perspective, which is that the solar system is not at all the typical system in the vicinity of the sun, or for that matter, the Milky Way. And the first way in which that is true has to do with the star. So we're orbiting a star called a G-type star, or a sun-like star. And this is a relatively large star compared to a census of stars near in its vicinity, as we'll see in a second. But what's even more interesting is its architecture, or another interesting aspect of it is its architecture. We have these very numerous and quite diverse terrestrial planets, of course followed by the gas giants, and finally, to top it all off, the ice giants and the outer bodies. But if we zoom out and take a look at the sun and ask the question, okay, what is the population or the initial mass function of stars, that is the distribution of stars in the vicinity of the sun within 30 light years look like? What are the most common types of stars around it? And you'll actually find that it's not the A stars, which are about twice as large as the sun. It's definitely not the F stars, which are about 1.5 times as large as the sun. It's not the G stars, which are exactly the twins of the sun. There's about 20 of those. It's not the K stars. They're becoming more numerous. There's about 44, but still not the majority. But it is this preponderant type of stars called the red dwarf stars that in the vicinity, within this 30 light year circle, make up 283 or 75% of all the stars in our vicinity. And so if we go back to our cross section of the solar system, one of the most beautiful pictures that has emerged from studying these planets in a population sense, is that actually the typical solar system in our galaxy looks more like this. Or the typical system in our galaxy has a host that is a red dwarf star. And what's even more interesting is that on average, we find that there are between 2 and 3 planets orbiting every single one of these red dwarf stars. That means that there are more planets orbiting these stars than there are around the more massive ones. Just for some context, around the more massive stars, you expect to find around only one planet. Now, that is not to say that this is the typical architecture of the system. In fact, architectures can be quite varied. And if you are interested, we can discuss in the Q&A. But this really begs an interesting question and an interesting point, which is that if we believe that the universe was fine-tuned for the emergence of life, then it for sure must be the case that for the most typical stars in the galaxy, around the most typical stars in the galaxy, the emergence of life must be basically a byproduct. In other words, if we want to if we want to support or find support for the anthropic principle in our data, we actually can go out and test it now by seeing if around the most common type of star in the galaxy, we can find planets with life-bearing potential. And this is particularly important right now because the next generation telescopes and instruments such as the Giant Magellan Telescope are currently in construction, and amongst their suites of instruments are included instruments, optical instruments, that are incredibly creatively made and have one goal, and that goal is to probe deep into the chemistry and physics of those terrestrial planets, those rocky planets that may or may not host life. But we gotta know where to point the telescope at. So the bottom line is right now, if we have this telescope in our hands, we might be a little bit hard-pressed to actually know where to look. So if we go back to our census of stars near the sun and get rid of all the stars that we don't care about anymore here, and we ask the question, how many of these systems in the vicinity of the sun, so again, within 30 light years, do we know to host terrestrial-sized planets? And the answer is going to be only 8. Actually, only 8. And it's not for lack of trying. Many of these systems, over 100 of these 283 stars, actually have been extensively studied. But we have yet to find planets around, terrestrial or rocky-sized planets around them. What's going on? What's up with that? Well, I think that the answers, those planets, are actually lurking in the noise of the data of a lot of the facilities that have been observing them for the past few years. It hasn't been that much time. These facilities have, to a great extent, only been working for less than a decade or so. But the bottom line is that they're probably out there. We need new facilities to do this. And that is exactly why I built the Tierras Observatory. Tierras is an observatory located in Arizona. This is about 40 miles from the US-Mexico-Nogales border. And actually, although it's a new observatory, it refurbishes a really old telescope called the two-mast telescope, which scanned the sky in the infrared back in 1997, I'm sorry. So what that means is that by the time I took the telescope over, it was completely mothballed. And so a lot of the beginning of my PhD had a lot to do with refurbishing the telescope, roboticizing it, and making it a state-of-the-art facility. And one of the things, the way that Tierras is going to go about finding these rocky planets is by using this thing called the transit method. Now, many of you may have heard of the transit method. It's a rather fun and intuitive method to explain. So as the story goes, if you have a star and there's a planet orbiting it, and the planet is in the right configuration with respect to you observers, that planet will generate a dip. And that dip gives you information not just about the presence of the planet, but also its size. Now, intuitively, as things go, that makes a lot of sense. But in reality, the problem technically gets quite hairy very fast. So what I'm plotting here is exactly what a terrestrial-sized or rocky planet, Earth-sized planet's transit looks like around a star that's about 30% the size of the sun. And what you would notice, if you squint your eyes enough, so basically if you say, okay, if there's nothing around there, I'm going to take the light from that star, and I'm going to say that star's light is 1. So then you ask the question, okay, by how much has that light decreased by when that planet is in front of that star? And you would know that you would be able to measure that the light decreases by 0.1%. And if 0.1% doesn't make any sense to you, let's go for an analogy. So imagine there's a ladybug. So imagine your terrestrial planet is a ladybug. And you want to look, you want to make sure that you want to determine whether this ladybug is orbiting around a lighthouse in San Francisco while you're observing it at MIT on a foggy day. So that's kind of the magnitude of the problem here. Now, the fog here is quite key because the fog represents the atmosphere, right? So I'm an astronomer. I just told you I built this observatory. I built it in the ground, so I got to look through the atmosphere. So the fog is the atmosphere. And so, first question that I might ask, or that you guys might be thinking is, okay, so didn't you just make the problem harder for yourself? So, because you added all this fog, but your lighthouse is actually in outer space. So why don't you just look at these planets from outer space? Build yourself a telescope and launch it and just see what happens. Well, in fact, we already have. So the MIT community already has. George, the PI, is sitting right here with us. So TESS is actually the premier, most fantastic facility to find the majority of these systems, or at least identify hints that amongst all those red dwarf stars that I showed you, there's going to be a candidate system that we really ought to be looking at and following up. But the challenge with TESS in the context of the terrestrial planets around the red dwarf stars is by design, right? So the TESS is a surveyor. The idea is to cover the whole sky. And so if you zoom in on one of the TESS cameras, you'll notice this is like the whole lens fairing. But really, if you want to zoom in into the aperture of the camera, what you'll notice is that the aperture of the camera has a 10-centimeter diameter. And what that means is that when you're observing these red dwarf stars, which are by definition fainter and smaller, you're collecting less photons. And again, photometry, the transit method, we're all about photon counting. So if we're counting less photons, then the spread, the error in our observations, the noise in our observations is going to increase. So TESS can get us hints with these red dwarf stars, but it cannot actually, it cannot, or it can, but it takes a lot of effort and a lot of those transit events to actually discover these planets. Okay, so what can we do? Are there other ideas? Well, I decided to use a bigger mirror where we can collect more photons and figure out a creative way to work around the fog. So here's how we work around the fog. I think the best way to explain this to you is to actually take you on a journey through the telescope. So that's what we're going to do. So first, we have a telescope mirror. So now instead of 10 centimeters, we have 130 centimeters, or 51-inch diameter. So choose your poison. So imagine you have, and then right underneath the primary mirror is what we call it, we have the Tierras instrument. So imagine you have light coming all the way from 30 light years away, sometimes even more, and then all that light's going to be focused onto your secondary mirror. Then it's reflected down through the primary hole through the Tierras instrument. And of course, this is a cartoon, but the first thing that light's going to find is a custom filter. This custom filter is really where the magic happens. So I designed this filter in order to inoculate the observations from the effect of water in the atmosphere. And the way we do this is by selecting for wavelength. We select only wavelengths in the atmosphere that are not affected by water, that are not affected by the effects of that fog. So after that light makes it through the atmosphere, it passes through a set of coded optics. And the idea of this coded optics is what we call a focal reducer and field flattener. The idea is that to increase the field of view of the telescope so that we have a lot more stars in the field. So that makes us both more efficient, but it also allows us to calibrate the observation. So to correct, for example, a passing cloud. And then that's really not unlike the focal reducers that you have in your iPhone pockets that allow for those wider images to be taken. It's just a bigger version. And then finally, we have a near CCD chip. It's what we call a near infrared quantum efficiency efficient CCD. So the idea is like we've really selected a CCD that's particularly good at gathering those photons from those red dwarf stars. So all together, this is what I wanted to show you what it took to build this observatory. So you can see me here with the engineers. We're working on building and assembling the whole observatory, the software infrastructure. This is the day that we installed the instrument. After we installed it, we realized the mirrors were misaligned by a lot more than anticipated. This is something that our predecessors never knew. So I had to spend a lot of nights actually aligning the telescope mirrors, solving all sorts of hardware and software problems, until finally we got our first light image. Wait, let me play that again, because I think just for.
Look at your cluster.
True, we did it. I promise you, I did not act that. That is the real. In very millennial fashion, I recorded that moment. But this is actually the first light image that we gathered from the telescope. Now, of course, I look at this image and I see tons of problems. But to the first-year grad student that thought about this for many, many years, this was fantastic. To the fifth-year graduate student that saw this image, there's a lot to work with. But really, we're here for the planets. We're not here for the pretty images of some nondescript cluster. So how are we doing? OK, so let me show you what a representative target, a 1 Earth radius planet, looks like through the telescope. And let me kind of try to paint a picture of how we can complement the effort that TESS is already doing. So over here we have TOI 2013. TOI stands for TESS Object of Interest. So this is a red dwarf star. It's about 30% the radius of the sun, and it's located 48 light years away. So it's a little bit further in that circle that I showed you. The discovery team that reported this detection actually reported a 1.1 Earth radius planet orbiting the star every 2.6 days. And this is going to become important in 1 second. And in order to do so, they had to use 18 TESS transits. So TESS delivered. It really delivered. It delivers, right? But they had to use 18 transits. And the reason why they could do that is because the planet has a very short orbit, right? So they had the opportunity to observe this 2.6, this transit over and over and over within the time that TESS observed this target. Now, with Tierras, with a single Tierras transit, you can see by eye that you can obtain the same this detection with the same level of statistical significance. So what that means is that for the temperate terrestrial planets, so for those rocky planets that are further from their stars, that are located in environments where the habitat might be a little bit more amenable, right? Then in those places where TESS may only give us a hint, we can actually more efficiently go and actually say, look, this is for sure a really interesting candidate to follow up with the GMT. So this is the magic of having observatories like TESS and then complementary facilities like Tierras. So with that, I want to finish up with what the next steps are, what I'm here to do at MIT. So what I'm here to do at MIT is really work on this, what we call the Tierras survey. And the Tierras survey really has 2 flavors. So on the one hand, on your left-hand side, we're going to be doing follow-up of test systems with candidate terrestrial planets. So basically like the one I just showed you. We want to intensely follow up systems where TESS has already found terrestrial or rocky planets, even if they are short orbits, because we know there are hints, there's knowledge in the literature and observational evidence that it is very likely that if you have a system where there's terrestrial planets very close to the star, it's quite likely that you're missing others further from the star. So that's one aspect of the Tierra survey. And then on the other hand, we're going to do follow-up of the red dwarf systems that TESS will not observe. And actually, if you want to see some of that data, you can ask me during the Q&A. I have some of that data. And this is cool, right? Because then what that means is that we can work towards a TESS completion survey. So we can work towards building a census of all the planets in the vicinity of the sun that are rocky and could potentially be life-bearing. But why haven't we started? Why does this slide say upcoming and not happening now? Well, the answer is actually mechanical. We have a serious telescope tracking limitation that I've been working on for the past 5 months. But we're making progress, and I'm about to show you the progress we're making. So what I'm showing here are 2 plots. Basically, the details don't matter. I'm showing on the top and the bottom I'm showing X and Y pixel positions. So these are the positions of our star on the detector every time I take images. And then that's on the Y-axis. And then on the X-axis, I'm showing hour angle. So picture this. You're following a star, and then you want to keep the star in the same position in your picture as you observe over the entire night, right? So hour angle, you can think about as position in the mount of the telescope. So what we want is that star to stay in the exact same place, because if it's moving around, that's really going to impact our observations. So what we would want is to have data that's literally aligned with 0. So there's no change in pixel position. This is what we have right now. So in blue, it's the original. All the colors is the original data. Every color represents a different data set, a different target. And you can see that there's this very systematic trend away from where we want the stars to be. But with this new guiding scheme that we are actively testing and working on improving, which are the white points, you can see that we have some semblance of improvement. So this is a highly challenging technical problem in terms of hardware and software, but it's all finally coming together to allow us to really go hard on our survey. So in summary, the solar system is not the typical system in our galaxy. Determining whether life is an inevitable phenomenon in the universe really does beget determining whether the typical stars in our galaxy could be life-bearing habitats. My team and I have built and are now starting to use the Tierras Observatory to increase the census of these terrestrial planets around nearby stars. And we are aiming to do so by leveraging tests synergistically in 2 different ways, by looking at systems that they have already said are interesting candidates and looking at systems that they will not be able to look at. And enriching this sample of terrestrial or rocky planets is crucial to know where to point the GMT at. And on a personal note, this is particularly exciting to me because that suite of next generation telescopes for the GMT is exactly what I want to be building once we leave Tierras in a very good leading place. Thank you very much.
Thanks, Juliana. OK, we have time for a bunch of questions. Neil, would you like to start? You're yielding to Paul.
Thank you for the wonderful lecture. I'm wondering, these red dwarf stars, the light is obviously far into the red.
Yes.
Does the atmosphere have a bigger or a smaller effect compared to light of higher frequency? I.e., do you have to do anything special about red?
Neil, what an insightful question. Thank you so much for asking that. So yeah, let's take a look. So I think this is a great plot to kind of summarize what you're getting at here. OK, so right here, let's actually go step by step here. OK, so right here I'm showing the spectra of a red dwarf star, here we call an M dwarf star, compared to the spectrum of a sun-like star, G star. So red is the M dwarf, it's in red. Yellow is the sun, is in yellow, right? So these are the spectra of these stars, right? And the color the color that you perceive that star at is, of course, dependent on the wavelength. And now, usually, what we do is we observe through, when we do photometry, when we do this photon counting, we observe through these filters. So typically, we observe through the Sloan I filter, which you see there in that contour on the left, or the Sloan C filter, which you see in this contour on the right. Now, the challenge with the water is the following. The water, so these are the water lines. So the water lines are changing the entire night as you observe, right? And so you're absolutely correct in your observation that the issue with the water is that because of the placement of those water lines with respect to the spectra of the stars, the water actually changes the color that you perceive from the stars differently. So you cannot so simply correct for it. But it's actually, we've demonstrated that it actually makes more sense to build a filter, going back to the idea of the filter, that actually ignores the water altogether by avoiding all those big water features, and still gets as much light from those stars, from those red dwarf stars as possible, so as far into the red as possible. Does that answer your question?
Yes.
Awesome.
Paul?
I know this is just a mechanical problem, but I'm interested to hear about generation 1 of the autoguider and generation 2.
OK, thank you so much.
What the shortcoming was.
So you guys you might be surprised to hear, but let me see if I have anything very helpful here to help you visualize. OK, I think this might be a good one. I'm not going to play it, but I'm just going to show you. OK, so the telescope is what we call an equatorial mount. So this horseshoe right here is what allows the telescope to move in this direction. Astronomers call that right ascension. And so Part of the problem with making the guider work better was that there were mechanical issues on top of software issues. So the first thing we had to do, so AutoGuider version 0 was basically using very old mechanical pieces on the telescope, the original ones. And it was having to do this weird workaround where basically you pointed at a star and then gathered some data. So let's say you exposed for 30 seconds. And then after those 30 seconds, you ask the telescope, OK, by how much has that star moved with respect to where you want it to be? And then the telescope would actually re-slew to the desired position, right? So it would actually calculate a new position for the star. But in this new version of the AutoGuider, we're using very different hardware in this horseshoe mount that smooths the movement of the telescope. And in addition to that, we actually enable the mode in the telescope. Again, this seems obvious, but it's actually very hard to implement, where instead of every time you want to reposition the telescope, you tell it to go to a new position, you actually only tell it to offset. So you say offset by this little bit in one direction, and then offset by this little bit in another direction. And it turns out that that algorithm is so hard to get right that most telescope vendors don't get it right. And so in the process of figuring out what was wrong with the telescope, we realized that the majority of facilities don't actually ever offset. They offset a telescope. They always re-slew to a new position. I hope that makes sense. Yeah. Thank you.
Other questions?
This is kind of a follow-up to Neil's question, but what is the reason for focusing on the red dwarfs and ignoring all of the other stars?
OK. So I guess the question is, your question can be answered pragmatically and scientifically. So let me start with the scientific perspective. So the scientific perspective is the following. If the most common type of star in the galaxy is the red dwarf star, and we want to understand whether the universe just naturally generates life, whether life is just a common phenomenon, then you actually would want to look for life in the most common type of star in the galaxy, just by in an average sense. Now, in a practical sense, the reality is that we're just lucky that those stars are smaller and they're less luminous. And so the transit of an Earth-sized planet around them is deeper, so you can actually access it. If you were to do the same thing around a sun-like star, facilities have been built to do it, but it's extremely difficult to do. No current facility can actually do that work. And then the other wonderful thing is that they're less luminous, and that implies that you can actually study the atmospheres of the attendant planets much more effectively. Yeah.
Okay, Wadi?
Yeah, thanks for the very nice talk. The TRS project is really exciting, and it's impressive how much progress you've made. I actually had a very similar question to Matt, but let me maybe reframe in the context of the first of your answers. So yeah. I guess the first comment is that I could imagine a universe where life, which is fine-tuned for life, but it all occurs on G stars.
Yeah.
And related to that, if you take the anthropic point of view, you would imagine if most life is on these red stars,
yeah,
and we would find ourselves on one. So I would imagine a very plausible scenario where, in fact, the universe has life, but it's mostly on G stars. So
that's true. Look,
yeah.
I think that's fair. So I think if I can rephrase your question, basically what you're saying is, well, even if we find life on G stars, then that still could indicate that we live in a universe that evolves towards life and mind naturally, and that still kind of supports the anthropic principle. I think that's fair, and that kind of goes back to actually the second part of Matthew's question, which is, okay, so what can we do pragmatically, right? So pragmatically, it is undeniably true that these red dwarf stars are just more observationally accessible. That is not to say that there are not people who are working on furthering the anthropic principle from the perspective of the G stars. It's just technically a very, very challenging problem. And then the other thing that you can say from a numbers perspective is, OK, so let's say we just focus on the G stars. I showed you there's only 20 G stars close enough where you can actually where close enough that you could actually not just find those planets, say those planets are there, but also say something interesting about the atmospheres of those planets. So you might be in a situation where, so maybe a better way to say it is that, in my opinion, the more effective way to use the search for life as a means to further the question of to further the debate of the anthropic principle is through the red dwarf stars than through the G dwarf stars. Does that make sense? Cool.
Okay, Juliana, thanks very much.
Yeah.